Welcome to ATMOS 5000, Day 11. Our objectives for today are coming from Chapter 4, Sections 4.3 and 4.4 from the Stull textbook. We'll be defining a total water mixing ratio, and we will be defining precipitable water. We'll derive the moist adiabatic lapse rate, and we'll introduce the concept of the equivalent potential temperature. So previously, for moisture variables, we had mixing ratio and water vapor pressure. And now what we're focusing in on is trying to get the total water mixing ratio, which includes the mixing ratio R plus the mixing ratio from the liquid component of the hydrometeors plus the ice component of the hydrometeors. So the total water mixing ratio includes all of the water vapor, the liquid water, and the ice, R plus RL plus RI. And secondly, we're introducing the concept of precipitable water, which is the amount of water that is in a column of air from one pressure level to another pressure level. And the precipitable water, dW, is defined as the average total water mixing ratio over that layer times the difference in the pressure between the bottom and the top divided by gravity and divided by the density of liquid water, which is 1,000 kilograms per cubic meter. So we've already covered how the temperature of an air parcel will change if it is a dry air parcel. It'll follow the dry adiabatic lapse rate. But now, if we are lifting a saturated air parcel, condensation will occur as the air parcel is lifted. And condensation will release latent heat energy to the environment and will warm up the air parcel relative to the dry adiabatic lapse rate. So here in this diagram, you can see that we have a parcel that has essentially a cloud base at 1 kilometer. For reference, we have the dry adiabatic lapse rate in a dashed black line, and blue is the saturated adiabatic lapse rate. And you can see that as you lift this air parcel, the temperature difference between the saturated adiabatic lapse rate and the dry adiabatic lapse rate is the heating of that air parcel that is occurring through the latent heat release through the condensation process. And initially, there's a lot of energy that is released, so the difference between the temperature of the saturated parcel and the dry air parcel grows quite quickly. But after a while, most of the water vapor has condensed out, and the saturated adiabatic lapse rate will eventually converge and be parallel to the dry adiabatic lapse rate because there's no additional latent heat release because most of the water vapor has already condensed out. The saturated adiabatic lapse rate, therefore, is always going to be greater. The saturated adiabatic lapse rate is a lot more complicated than the dry adiabatic lapse rate. So here we define the saturated adiabatic lapse rate, gamma S, as minus delta T over delta Z for saturated air parcel. And you can see that it has the gravity force divided by C sub P for the saturated air parcel. And then in the numerator, we have a term 1 plus the saturation mixing ratio times the latent heat of vaporization divided by the specific gas constant for dry air times temperature. And then in the denominator, we have those same variables, but the latent heat of vaporization is squared, as is temperature, and then we also have the C sub P sat. And just as a reminder, to calculate the C sub P saturation, it's going to be equal to 1 minus the saturated water vapor mixing ratio, R sub S, times the specific heat for dry air at constant pressure, plus the RS times the specific heat of the water vapor at constant pressure. That's the way that we normally deal with the saturated adiabatic lapse rate, but it can also be defined as a delta P over a delta T over delta P as well. So you'll see how the temperature changes with pressure. And once again, it has those same variables in it, but it is also a function of pressure is the additional variable that we have in the denominator there as well. So referring back to the skew-T diagram, so recall that on the skew-T we have temperature on the x-axis and pressure on the y. And on a skew-T, the temperature, the isotherms, are slanted up and to the right. Now, one of the lines on the skew-T that we haven't really talked about yet are these moist adiabats, which are these dashed brown lines. And these are, in fact, the saturated adiabatic lapse rate that was shown in the previous equations. And eventually, if you take these far enough up into the atmosphere, they will become parallel to the dry adiabats for the reasons mentioned before. So, let's put it all together. And how does the temperature of an air parcel change when it is lifted? So we're going to start off with an air parcel that is 20 degrees Celsius at the surface, and it's unsaturated. So as we lift this air parcel, its temperature is going to decrease at the dry adiabatic lapse rate, and it's going to get colder. By the time it reaches 1 kilometer, it'll be 9.8 degrees Celsius cooler than what it was at the surface. And at that point, in this scenario, that's where the lifting condensation level is. And if we lift that air parcel above the lifting condensation level, it will follow the saturated adiabatic lapse rate and not the dry adiabatic lapse rate, which is shown as the dashed black line there. So the relative humidity in the layer below cloud base is going to be less than 100%. And the relative humidity in the layer above cloud base is going to be greater than 100%. So what is the lifting condensation level in this scenario? And where is the cloud going to be? The cloud base will occur when we deviate from the dry adiabatic lapse rate and switch to the saturated adiabatic lapse rate. We define that as the lifting condensation level. So you just saw how we derived the equivalent potential temperature, and what I'd like to do here is to use a skew-T diagram to show a graphical way that you can use to calculate the equivalent potential temperature. So we have an air parcel at 85 kilopascals. It has a temperature of about 12.5 degrees Celsius and a mixing ratio of 6 grams per kilogram. So it starts off with a temperature that is located there at the blue star, and the mixing ratio is at the yellow star. And as we lift that air parcel, its temperature will decrease at the dry adiabatic lapse rate, while its mixing ratio will remain constant. And when those two intersect, that is the lifting condensation level. And then as you lift that air parcel higher, it will follow the moist adiabat because it's following the saturated adiabatic lapse rate. And we will continue to lift that air parcel all the way up to essentially the tropopause. And at that point, the saturated adiabatic lapse rate is parallel to the dry adiabatic lapse rate. And then what we do is we assume that we have condensed all of the water out and that that water has been removed from your air parcel. And then you bring that air parcel all the way back down to the surface following a dry adiabat. And you don't bring it all the way down to the surface, you bring it all the way back down to 100 kilopascals or 1,000 millibars or 1,000 hectopascals. And the temperature to which this air parcel that has gone through this pseudo-adiabatic ascent and descent all the way back down to 100 kilopascals, that by definition is your equivalent potential temperature. And the difference between the potential temperature and the equivalent potential temperature is the maximum heating that could be achieved through the latent heat release of an air parcel, assuming that all of the water vapor condensed out. So the equivalent potential temperature is conserved for dry and moist adiabatic conditions. And as I just stated, it provides a measure of the maximum amount of heating which can occur through condensation, but it does not include the latent energy release from freezing. So it does not represent the absolute maximum amount of heating that could come through cloud processes, because you could get an additional bump in latent heating from the freezing of the liquid water.